Okay, let's look at number 6. The table shows the deposits in Australian dollars made by Vicky in an investment account on the first day of each month for the first 4 months in 1999. The interest rate is 0.75%. Now if I move my decimal over twice to convert it into a decimal, please, that means 0.00127.5. There we go, now I've moved the decimal twice and converted it into a decimal. So let's think about what's happening. My $600 deposit from the first month of January is gradually earning interest each and every month. So as we move forward into the month of February, it will have been increased by 1 plus 0.0075. And again as it moves forward into March, and again as it moves forward into April, and then the same thing's happening with February as it moves forward into March and onwards into April and so on. Now right now in part A we only need to show that the amount of money in Vicky's account at the end of February is, well, that amount. Now because it's a show that question, I'm going to ignore my answer, pretend it's not even there, and I'll check my work afterwards to see whether I got an answer that matched. So let's look and see what's happening then. Our January amount of 600, so this is at the time of January 1, and then here's February 1, and then here's, let's say, March 1. The 600 had to multiply by 1.0075 in order to get the amount it's worth on February 1. And then it has to multiply by that growth rate again. During the month of February, it's also earning this 0.75%. So we can see then that the total amount of money from our January deposit has grown by taking our 600 and multiplying by that growth factor twice, that is to the power of 2, because we had to multiply by it to represent the growth during the month of January and during the month of February. That takes us to the end of February. She also made a deposit of $1,300. Oops, I've drawn this in the wrong place. Our $1,300 deposit actually occurred in the month of February, February 1. So that's when the $1,300 came, on February 1. And the $1,300 needs to be multiplied by 1.0075, but only once, right? So this total value, 1,300, has only had a growth factor of 1.0075 for 1 month, that is to say during the month of February. So now we just got to add these two quantities together, and we'll end up with the total amount of money in her account at the end of February. So we've got 600 is multiplying our 1.0075 to the power of 2, representing that it's been growing for 2 months. And to this we need to add our $1,300 deposit, which has been growing at 7.5% for only 1 month. I can raise it to the power of 1, but it doesn't really change anything. And we see that the total amount of money that Vicky's got is $1,918.78375. 78375. IB will often want you to show the unrounded answer before then rounding to the financial value, where we always go to 2 decimal places. And if you check, that is indeed the exact answer that we were expected to get. Part B, we now have to calculate the amount of Australian dollars in her account at the end of April. So we're really just doing the same process, except we're extending it by another couple of months. So our 600 that we deposited at the beginning of January has now got 4 months in which to grow. That is to say that it's growing through the months of January, February, March, and April. The $1,300 deposit that we put in on February 1 has got 3 months to grow during the months of February, March, and April. The $230 deposit that we put in at the beginning of March has got 2 months to grow during the months of March and April. And lastly, our April 1st deposit of $710 has only got 1 month in which it can grow during the month of April. I want to add these 4 values together, and the sum should represent the amount of Australian dollars in her account at the end of April. So here we go. 600 times 1.0075, which is being raised to the power of 4. To this we want to add 1,300, and the 1.0075 this time is being raised to the power of 3. To this we want to add our $230 deposit, which has only been growing by 7.5% for 2 months. And lastly, we've got our $710 deposit, which has only been growing at a rate of 0.75% for only 1 month. And her total amount of money then is 2,896, and if I round to 2 decimal places, 0.46 Australian dollars. And as always, we can round to the nearest dollar, 2,896, or even to 3 significant figures, which would be $2,900. Now the question continues. Let's suppose that she makes no withdrawals or deposits after the 1st of April. So that means that her last deposit was that $710 deposit. Well, we know what's happened by the end of April, or should I say May 1 is close to... Maybe I should just write it out as the end of April. That's going to be a little clearer, I suppose. So the end of April, we just worked out that she's got 2,896.46. We want to find out what's happening until we get to the end of December. Well, presumably, because of the end of April to the end of December, there's 8 months. It means that our amount of money is going to be multiplying by its interest rate monthly a total of 8 times. That represents a growth through May, June, July, August, September, October, November, December, taking us to the end of December. Now each growth rate we know represents a times 1.0075. So that means that our 2,896.46 is multiplying by this growth factor over 8 months. So we'll take 2,896.46 and we'll multiply it by 1.0075 being raised to the power of 8. And we end up with an amount of 3,074.88 Australian dollars. As always, you could round this to the nearest dollar, 3,075, or to 3 significant figures, 3,070. Now it says from the 1st of January, so that is basically right after this whole process has finished. So the 1st of January, the bank applies a new interest rate of 3.5% per annum. So this is the amount of money that we have at the end of December. I'll just write it again. 3,074.88. So that's basically, I guess you could argue, is the amount of money that we've got on January the 1st of the year 2000. The next day we still got that much. It says, in how many full years will Vicky's investment first exceed 3,300 Australian dollars? So our 3,074.88 is now undergoing a new interest rate of 3.5%. And I want to figure out what is the number of years it will take in order to have grown to at least 3,300. Now because it says full years, we know that n must be an integer. And we learned earlier on that the best way to solve a problem where the variable that you're looking for solve for, you know it's an integer, best way to do it is with a table. So let's go into our y equals, and we're going to create a brand new equation of 3074.88, which is multiplying 1.035 raised to the power of x. Let's have a look at the table. So we want to find out how many full years did it take to pass 3,300. And when you're using a table to show your work, we only need to show the row before and the row after it actually passed. And so we know that we're dealing with y1 equals this function. Let's just include that information. And now in the table, we'll have our x, and we can see that when we were at 2 years, we didn't quite have enough. Our y1 function was only equal to 3,293.9. But by the time we got to the end of the third year, we've now passed that 3,300 threshold and gone to 3,400 even, well above. And so the answer then is 3 full years is what it takes in order to finally have more than 3,300. Question number 7 will be quicker. We can see the first 4 terms of the arithmetic sequence. We need to write down the nth term of the sequence. Well, first of all, we can see that our u1 is equal to 1. Furthermore, it's pretty quick to see that d is equal to positive 4. We are always increasing by 4. We know that in an arithmetic sequence, our nth term can be described as the first term plus n minus 1 times the common difference. So let's substitute. un equals 1 plus, it's an n minus 1 times 4. Now I suppose you could try to simplify this a little bit if you cared. We could distribute the 4 to both the n and to the negative 1, giving us a final expression of 4n minus 3. But I don't think that IB would really care whether you left it in this form or simplified form. So there's part A. Part B says that we need to calculate the 100th term of the sequence. Well, we know that the 100th term of an arithmetic sequence can be taken by finding the first term and then adding it to 1 less, 99 in this case, of the common differences. Our u1 is 1, our common difference is 4, and if you add 1 plus 396, we'll get an answer of 397. Number 8. Geometric sequence, all of its terms are positive. The first term is 7. Well, that's nice information. The third term is 28. Now, there's a couple of ways that you can think about doing this problem. One way is that you could think about your missing u2. Realize that to get there in a geometric sequence, we've multiplied by r, and we have to multiply by r again to reach 28. This would show us then that our 28 is found by taking our original term 7 and then multiplying by r and then by another r, that is to say r squared. Another way you could come up with this equation, though, is to recognize that in a geometric sequence, because un is equal to u1 times r to the n minus 1, your u3 will be equal to u1 times r to the power of 2. In our case, our u3 is a 28. So our u3 can be changed for a 28, and our u1 we know is 7. And look, we've come up with the exact same equation, just 2 different ways of thinking about how to get there. Let's divide both sides by 7 now, in order to get the r squared alone. 28 over 7 is equal to 4. If we try to get the r by itself, that means we need to take the square root. And when you take the square root of both sides, we need to include a positive negative. This means that r is equal to positive or negative 2. But let's think for a moment. If r was equal to negative 2, I'd have 7 times negative 2 to get my second term. That would give me negative 14. But we were told that all of the terms were positive. So we have to throw out the negative value of r and keep only the positive one, such that all of the terms in the sequence will be positive. It says find the common ratio. We just did it. Therefore, r is equal to 2. Number 9. The rate of inflation from the beginning of 1995 has been 4.5% per year. Part A. A loaf of bread cost 1.70 on January the 1st, 1996. What did it cost exactly 3 years later? So the cost of that loaf of bread has been increasing by 4.5%. I've just written that as a decimal per year, and it's been taken 3 years. So that growth rate is occurring for 3 different years. Let's work out what we get. So 1.7 multiplied by 1.0045 to the power of 3. And the cost of the loaf of bread now is well, I'm really surprised. Oh, I see. I entered it in wrong. This amount here, let's do it again. I should have had 1.7 times 1.045, not 0045, raised to the power of 3, and there we go, that's more what I was expecting. $1.94 if I round to the nearest cent. Part B. A car cost $40,000 on January the 1st, 1999. What did it cost exactly 2 years earlier? Now, you might remember that we did a problem like this earlier on, where we took our initial cost of $40,000, and it's increasing, right? It's inflation, so we've got 1.045. But because we're looking 2 years in the past, we make it to the power of negative 2. So 40,000 times 1.045 raised to the power of negative 2. And that gives us an answer of 36,629.20 when I round to the nearest cent. Another way you could have done part B is by thinking about, okay, we've got some unknown value, let's call it U1, which represents the price of the car in 1997. And then a couple of years later, by the time we get to U3, we will now be at 1999. And we know what the 1999 cost is. It's 40,000. So our U1 cost has had to multiply by the R value twice. And we know that this R value is 1.045 because of the 4.5 growth rate. So we could take our unknown value U1, multiply it by our 1.045 to the power of 2, and that will give us the car's price in 1999, 2 years later. So our 1997 price has grown by 2 years to get to the 1999 price. So in order to get U1 alone, I'm going to need to divide both sides of this equation by 1.045 to the power of 2.